HVAC 360 is brought to you today by the letter P. All hail the letter that brings us words like pressure, pumps, and everybody's favorite, payday. We just want to take a moment to remind you that other words also begin with P, like phenolic, photovoltaic, pneumatics, and lest we forget, psychrometrics. Letter P, thanks for all that you do. Paid for by the Council of Not So Simple English. Hey, what's up, everybody? Welcome back. This is episode number 92. Matt Nelson here, your host for HVAC 360, helping you go further and faster in the field of HVAC. In this podcast, we share stories, interview industry experts, and help you add some best practices to your HVAC toolbox. If you haven't already, and this is your jam, why don't you go to HVAC360.com and join my growing mailing list, where every Friday I send out some more stories, play some games, a little photo flaw game, and share some learning opportunities. And that is served up on a weekly basis. The best part, I keep them short. So, what's up for this week? This week I wanted to share some advice and best practices surrounding the duct sizing methods. I may mention a couple of things regarding design and layout, but I'm going to save that for another episode. And we'll get to those best practices and advice right after a brief word from our sponsor. So one of the first tasks that I was given as a young engineer was to help an older engineer do some ductwork sizing. Seems simple enough. He had laid it all out for me. He had listed the CFM on the plan, and he had kind of slid it over, and he says, okay, what I want you to do is I want you to size this ductwork. And I want you to use your duct sizing calculator. So I was doing this all by hand, and the duct sizing calculator is nothing more than a duct sizing wheel. So it was a little wheel that kind of equated velocity, pressure drop, and duct sizes, and you kind of match those all up. It's pretty easy to get a hang of, and I know that the one that I was using was a Cook. Other things, Trane also has a trademark one they call the Ductulator. It's a combination of a duct and calculator, so Ductulator. So I might be referring to those as ductulators, just inadvertently. It's like Kleenex for our industry. And he gave me the instructions of, okay, take the ductwork, you get the CFM, and you line up the pressure drop. And for supply ductwork, we wanted to use 0.1 inches of static per 100 feet of ductwork. And you size that up, and then you go over here and you select the dimensions for the duct, and then you write those on the piece of paper. If it's the return, then it's going to be a 0.08, and we kind of made little marks on the two indicators that I was going to use, but 0.08 for the return ductwork per 100 feet. And that was, he kind of set me off on my way to go. So I, raring to go, got all that calculated, took it back to him. I'm like so proud. I'm like, here you go. And he looks at it and he looks at it and he's like checking some of them. He's like, some of these are not, they're a little bit off. It's like, why is that? And it was the fact that I was using the Cook calculator and he was using the Trane Ductulator, and they weren't exactly the same, which, in my mind just kind of, blew my young engineering mind. Like, okay, it's a calculator. Numbers should be numbers, right? Use the same thing. But for whatever reason, the duct sizing calculators are a little bit different. So I guess, just something to note, if you're, as a company, you have certain standards and you do design and you size ductwork by hand, why don't you make sure that everybody uses the same ductulator? So that certainly helps. And, and in reality, I kind of look back on that as I was doing some research for this episode, and I realized, using that 0.1 inches of static per 100 feet of duct, that was a little conservative. I mean, engineers like to be conservative, but I might have ended up oversizing a lot of ductwork. I guess on the other side, I end up saving some energy as well, inadvertently, and I just didn't know that. And that's the thing. I just didn't know a lot. It was just, okay, here's your tasks, here's how to do it, go to town. And I did that. So for the longest time, I didn't even know, that there were any other duct sizing methods. It wasn't until I took educational course a number of years later where I discovered that there were actually 3 different methods. And I'm like, what? I'm like, did I not get the memo? Why was this, kept from me? It should be obvious that you should explain, okay, here's what you're using. You're using the equal friction method because all the different pieces of ductwork that you selected are based on a certain friction loss. But there are others that were out there. And generally speaking, 2 are the primary ones. A third one called the velocity method or the velocity reduction method is kind of the third one that you find in Train and Carrier. You don't find it in ASHRAE so much. ASHRAE focuses on the equal friction and the static regain method. And I found out in Train kind of why that was. I guess the velocity method is really more of a residential practice. And Carrier had that velocity reduction method, and I'm not sure that varies too much from the regular velocity method. But in this one, I'm going to focus pretty much on the equal friction method I got to imagine is going to be the most common. They did note that the static regain method that was used for larger applications, large height rises, things like that, where you would end up using that. And looking with this, funny enough, I get back into the fundamentals, ASHRAE fundamentals manual, the handbook that they have, and it did not disappoint. It was as difficult to use and not friendly as usual. I mean, the very first page, they hit you with integrals, they hit you with numbers of equations, and I'm like, this is not a practical guide. Train and Carrier do a much better job. They're much more kind of friendly. But in ASHRAE's defense, I mean, this is kind of a definitive reference. So it has everything and the kitchen sink, but it doesn't have a lot of space. So they're kind of tasked with, okay, here's duct design in 33 pages. And don't forget, you have to put in the tables, charts, and a reference section. You have 33 pages to describe duct design. And that has to be a pretty daunting task and weeds out a lot of helpful, useful examples. Here's one example, here's another example, done. So that's in ASHRAE's defense, I think that's what you get. But you certainly understand the theory behind duct design. But I think that Carrier and Train again do a much better job practically teaching duct design to younger engineers. All right, so what's really the behind these methods? What's the goal? Obviously, you're delivering air through ductwork, and you're delivering heating or cooling. And I guess as far as duct layout goes, you need to make sure that you keep in mind that you want to use as little material as possible. Not only that, but you want to make sure that the fabrication and installation costs are as low as possible. So keep it simple, keep it practical. Don't get crazy. You want to keep the pressure drop low. That's important for your fan sizing. That leads to lower energy drop. Smaller ductwork obviously also leads to a low energy loss. You want to have a low leakage, so that comes into play, but that's, it depends what size the ductwork is, where it is in the system, and then, low noise. Obviously, that's a big one when sizing the ductwork. A little bit more in how you lay it out. That can play a big factor, but when you talk about velocity, that can add a lot of noise in a system. So also, and I guess the big thing, when you talk about layout, you need to make sure that it fits into the building with the rest of the systems and finishes. So that's really the why that you need to focus, why it's important to understand duct sizing and understand the nuances of duct sizing. All right, so let's get back to these 2 methods, these equal friction method and the static regain. What's the benefits of these? Using the equal friction method, this is typically going to be a lower first cost because of your smaller branch ductwork. The static regain, I guess Carrier did a nice example in their manual. Saving energy is one, and we're talking like in the neighborhood of 5%, 6% was the example they used. And it ultimately needs less balancing because everything is kind of, a lower pressure drop. So it's easier to balance. I totally understand the static regain. That's simple. The velocity method, that's simple as well. You base it either on a pressure drop or you base it on the velocity. The static regain, not so much. I was hoping that I'd get a better handle and understanding through the research that I did, but I just didn't. There wasn't some, great examples. And I think that maybe stems from the fact that typically you use static regain in larger systems, and in those larger systems, you'll tend to use sizing software. So it makes it easier, and you don't have to understand it. But ultimately, I guess maybe given it the old college try, what the static regain method is it tries to balance out the downstream pressure drop with the upstream pressure drop, and I guess the downstream being downstream of the VAV versus upstream of the VAV box or terminal unit. So that is really what it does. It tries to oversize the supply and branch ductwork upstream of the VAV, so it reduces that, and it tries to balance that out with the VAV box and downstream of it. So if you take a look at the two side by side, the equal friction method and the static regain, the mains are primarily they're going to be sized similarly. You're not going to get too much difference there. The difference comes in the branch ductwork, which again, that's why it's lower first cost for the equal friction, smaller branch ductwork, but more energy savings, less balancing because you have larger branch ductwork with a static regain. All right, so I hope I didn't mess that up too much. If it's still confusing to you, do your own research on static regain if that's something that you're into. All right, and then I want to just wrap this up with some best practices that I kind of went over or discovered in my, from my experience and based on what I was reading. So when you're talking about duct sizing, velocity recommendations, there are charts depending on where you look, and might be something that you would develop a company standard on. Here's the sizes that we're taking a look at, or here's the velocities that we're going to use in these certain situations. Some of the ones, it's similar to like a 500 foot per minute for coil velocity. Why 500 feet per minute? If you didn't know, it's to prevent carryover. You just want to keep the moisture that condenses on the coil. You want to allow it to drip off. If you go higher than 500 feet per minute, and frankly, again, that might be conservative, so it might be 550, might be 600. You start to get some moisture. You get some carryover. So moisture will start being blown off the coil at higher velocities. So that's why you want a coil, an air handling unit, at 500 feet per minute. If you're talking about the duct mains, if you're talking about like an office building, in an office building, you're probably going to have 2,000 feet per minute in the main. And that was something that Carrier recommended as a maximum. Obviously, you can keep it lower if you want, but that you kind of, it's the balancing act between being noisy and efficient and using energy, and again, it's all gets back to those some of those things about why we design it. Is the pressure drop and the low energy usage and the fabrication and keeping it simple. For branch duct work, you want to limit it to 600 feet per minute in offices. And if you take a look at that versus what you'd have in a residential application, they're going to be like less than half. Residential, you want to keep it slow, 1,000 feet per minute in the main supply run, and 600 feet per minute in the branches. And again, that's a combination of noise, and it's a combination of your fan sizing. Again, if you don't have a big fan, you're going to have to oversize your ductwork because it just can't handle that much static pressure drop. And obviously the layout and the fittings play a large role in that. But that's something that you have to be very cognizant of in sizing your ductwork. Will I have enough? Will I have a big enough fan to overcome this? And I guess you want to be able to start somewhere safe, so when you get to the end, it's not going to be out of proportion. That's where some of these velocity recommendations come from. Also, other best practices: use round ductwork whenever possible. Aspect ratios for square ductwork or rectangular ductwork, you want to keep those 2-to-1. So if you have like a 24 by 12, that would be a 2-to-1 ratio. And you want to have an absolute max of 4-to-1, and absolute max, that's coming from me. I wouldn't trust anything that was over 4-to-1 aspect ratio. So again, using that our example, that would be a 48 by 12. And obviously, as you get smaller and smaller, that aspect ratio of 4-to-1 becomes more and more unacceptable. I wouldn't have something, a 40 by 10 piece of duct. To me, it seems just, at all possible. But obviously, there's these installation and layout factors that come into play. But try not to get that kind of out of whack with your aspect ratios. And obviously, one thing that you want to keep in mind is that there's different lengths. Typically, your rectangular ductwork is going to come in 4, 5, or 6 foot sections, and those are going to be stacked up. If you use round ductwork could conceivably be much, much, much longer. And actually, I found a video on YouTube that I'm going to share in the show notes of them making like a spiral round ductwork, and you can make those seriously long. Really, the only factor is transporting them from point A to point B. If you did it on site, which, if you had a big enough project, maybe you just do that. But for, that, you might have, an easy, maybe like a 10-foot section or a 12-foot section. Easy for a spiral duct. And obviously, the fewer fittings that you have, the fewer joints that you have, the less duct leakage, the less extra parts you have, the easier it is to put up. So there's a lot of benefits for being able to select round versus rectangular. If you've never seen rectangular duct being put together, I'd also go to YouTube and try to find some. I didn't see a lot of great examples, but if you don't know about duct construction, it's something that you should definitely take a look at, just to understand the appreciation of what you're designing, how these things are being put together. Other things, roughness factor, very important. So once you lay it out, you're assuming that the roughness factor coefficient really is, for brand new ductwork, brand new sheet metal, it's 1. So it doesn't increase your size or decrease your size or affect your pressure drop too much. But when you get into things like when you have real smooth sheet metal, you might get a bonus for the smoothness factor versus what the pressure drop is. If you're using a concrete tunnel for your ductwork, and that certainly happens in larger buildings or different theaters that I've seen, where you have just concrete walls just kind of encasing it, and that is increasing your friction. And that's slightly, that might be, for the concrete, it could be a big factor. Generally speaking, I think the big killers there is the flex duct work. When you look at the flex duct, it really, really affects the pressure drop. And when you're going from, 0.1 inches of static per 100 feet, and you have a flex duct that is 1/4 of an inch because it's compressed and it's improperly installed, that's huge. I guess the flex duct, you want to be able to kind of minimize the length. You don't want to use any more than you absolutely have to. You want to be able to make sure that you're watching for tight areas. And if you're inspecting it out in the field, you want to make sure that those connections, and typically they're going to be from a main trunk to a VAV box or a branch duct to a diffuser. Those are kind of some of the typical places that you see them applied. And if you compress it, if it's not fully extended, you're going to get a lot of pressure drop. And I've seen, a lot of cases where they just tried to do, they didn't lay out the system real well, and they tried to make it up with flex duct, and that's not going to work. And then, of course, obviously, I think we've all seen horror stories where, you have one single plenum and all this, just tens of, a bunch of, 10 foot, 20 foot of flex duct just kind of, it looks like this giant spider going all over the place. That is a huge pressure drop. So especially when you're kind of fighting against a fan that might be a little bit smaller, if you've used that a lot in residential applications, you just won't get anything out of that duct run at all. I guess the last thing I want to just point out, best practices, line duct work, and just make it clear that line duct work is just typically when you have a duct size on a plan, that is going to be free area. So that is not incorporating any sort of internal lining. So you're going to, and this is kind of, I've seen it play out a number of times where the contractor will take it verbatim. You say you have a 24 by 12 duct on this drawing, and it will be 24 by 12 in the field with 1 inch of internal lining. And you're like, no, that was 24 by 12 internally lined. So that was a free area. So it has to be one. If you add the lining, you have to increase the size. And, you get into a bunch of fights, and, can you, handle the pressure drop? Do you take it out? Do you make them redo it? It becomes a lengthy discussion point. So if you make it clear on the drawing with a big hairy note that this, in fact, is clear area, regardless of whether it's lined or not, the free area, that is probably the best policy to put on your plan. And again, if you didn't know, 101, if you look at a plan and you see a 24 by 12 duct, that is a 24 wide by 12 deep duct. The first number on a plan is always going to be the plan number, is always going to be the plan dimension, and the second one will be the depth. So those are some of the things that you want to take a look at. All right, that's a wrap for this week. Thank you for your time. I greatly appreciate each and every one of you listening. You are the best of the best out there. I know. I hope this was helpful. If it was, let me know. I could even do a course or a video or something like that if you are interested, and contact me directly. If it was something that, if you know somebody that is interested in ductwork design, why don't you go ahead and share this episode? It'll increase the value of the relationship that you have with that person. And also, as I mentioned at the top of the show, please, if you do one thing, join the growing community at HVAC360.com for all that bonus material. And if you do something else, I would greatly appreciate a iTunes review and a comment. Anybody who leaves a comment, I always give them a shout out on the show, just as an extra bonus. So I appreciate that. Well, that's a wrap for this episode of HVAC 360. I'm your host, Matt Nelson, helping go further, farther, faster in the field of HVAC. And as always, remember, know what you build and share what you know.